So here we are at torque, and torque is it's the first time really, I think, in rotational stuff where we have, well, not the second time, but it's a situation where it's a completely different thing, and if you were a novice, you wouldn't necessarily guess that torque was the angular equivalent of, or rotational equivalent of force. Colloquially, I think of it in terms of rotational force. It's the turning effect of a force on a lever arm around a turning axis. So it's quite specific. You can think of it in terms of a door. If I push near the crack on the door, I will have a more turning effect than if I push it on it near the hinges of the door. Both are possible to undo the door, but I would need to get the same angular acceleration that I want to cause the door to start opening. I would need to push a lot harder when I'm nearer the hinge than I would do when I'm further away from the hinge. And try it at home. Just go home and try it. And so the actual location that the force is applied matters. And so here's a picture of a wrench, and it's not a great picture, but it'll do for our purposes. So here's a picture of a wrench. Here's the turning axis in red, and then we're applying a force. And intuitively, we kind of know to pull on a wrench at 90 degrees to the handle. You kind of know, when you're doing something, you pull like that at 90 degrees. But you can't always. In fact, I remember my first car was simple enough that even as a novice driver, I could actually have a go at maintaining it. Because it was literally looked like the diagram of a car engine in my physics textbook. I opened the hood, and there was a cylinder block, and there was a starter engine, and there was the flywheel. And then over to one side was the carburetor, and over to the other side was the exhaust manifold, and there was a battery and an alternator, and that was it. There was nothing else. And so I looked at that and, I need to do stuff. And I can remember I had an old car. I inherited it from my father, who bought it before he passed his driver's test, and he never passed his driver's test. He was 50-year-old guy, and he just never got through. It was the British. I took the test 3 times before I passed in Britain. Often when you're doing work on car engines, you can't get your fingers at 90 degrees to the actual wrench. You've got to kind of put the wrench on, and then you've got to sleep your hand in, and you kind of push in with your fingers upwards. And you realise it's much harder when you're not at 90 degrees to actually turn something. I mean, do it. Put a ruler down and push on it and pull at 90 degrees, and then pull at an angle. Get a piece of string and pull at an angle. It's much harder. And so the turning effect is given by the lever arm, which is R in this case, multiplied by the perpendicular force. That's the turning effect. It's that force times that lever arm. That's what you're looking for, a right angle. And the problem is I'm not going to give you a right angle. I'm going to give you maybe that lever arm, and maybe your force is not going to be at 90 degrees. And so you got a choice at that point. You got to take the component of the force that's 90 degrees to the lever arm. So your components are going to come back up. Or alternatively, you can take the component of the lever arm that's at 90 degrees to the force. Or you could pick another direction and take the components of each thing at 90 degrees to each other. You can mess with it, but in principle, you take the component of the lever arm, of the force at 90 degrees to the lever arm. There's your lever arm, and there's your force. So you find that component. Or alternatively, let's change colour. You take and you say, okay, I'm going to have the component of the lever arm that's at 90 degrees to the force. But you've got to take them at 90 degrees to each other. So it's not any old force and any old lever arm. Just like work was not any old force and any old displacement. In work, they had to be in line with each other. It's kind of interesting. We're still taking displacement and force, But in work, it was the displacement the force moved through. And now it's the displacement that the force is positioned at relative to the turning axis. So they're different animals, even though they're both force and work. Both force and displacement. And in this case, we don't want them to be in line. We want them to be at 90 degrees. And so we say, well, the tendency of a force to rotate an object about some axis is measured by the vector quantity called torque. And so what we should say is, and then I write it down not as a vector quantity, but it is a vector quantity. Vector quantity called torque. What Greek letter is this? Anybody? It's tau, T-A-W. Or T-A-U. That's probably T-A-U. But we call it, it's torque. And basically, what we say is vector torque is equal to R cross F. Now, there's a couple of things going on here. R cross F, which equals, I'm going to do it in the same order, it doesn't matter. R times F times the sine of the angle between. This is the magnitude of R, this is the magnitude of F, and this is the sine of the angle between them. So let's look back at our diagram. If that is my R, and that is my F, because that's originally what I was given, there's my angle. The R's pointing in that direction and the F's pointing in that direction, so that's the angle between them. Okay. So if I had a force like that, and I had a turning axis there, I would say, oh, okay, so there's my R, and here's my F, and that's the angle between them. Now, it turns out it doesn't matter, because if I take sine of 60 is, in fact, try it, sine of 60 and compare it with the sine of 120. Can you do that for me now? So front row do sine of 60, second row do sine of 120. Yeah, 60, yeah. So what does front row get? So what do you get? 0.866, and you're in degrees? Yes. Good. And what about the second row? What do you get? Sorry? 0.866. So it turns out if you make a mistake and you call that phi, it doesn't make much difference. Okay? But this is a vector. Although I'm talking about the magnitude of the thing here, because it's a vector, it's got a direction. And so how can a turning effect have a direction? Well, because we choose it to, I guess. And turning effects have a sense, clockwise or counterclockwise. And that clockwise or counterclockwise gives us a vector direction for it. And the way you do these things is you say, okay, I'm going to point with my fingers towards in the direction of the first vector. I'm going to then curl my fingers with regard to the second vector, and I'm going to look at where my thumb's pointing. So let's do that now. I'm probably jumping ahead a little bit, but that's fine. Let's say my R, my lever arm, let's say that I'm the turning axis. And my force is applied over there by the flag. That's my R. R goes from me to the flag. So point your hand towards from you to the flag. So do this. If you just look at me, you're just going to watch somebody doing something. So pick your right hand and put it in the air and point it towards the flag. Okay, good. And let's say that the force at that flag is pointing vertically downwards from the roof to the from the ceiling to the floor. So turn your hand so that you can then comfortably curl your fingers towards the second. So it's pointing downwards. So your fingers should be pointing vertically downwards. Okay? Which way does your thumb point? To your left, yeah? That's the direction that the torque is in. If you were to draw a vector torque, that's the direction this torque is in. Now let's see. Which way, if that is the case, which way will my lever arm turn? physically, if this is the wrench and I'm pushing on the end, which way does my lever arm turn? Does it go up like that, or does it go down like that? It goes down, doesn't it? Because the force is pointing down, yeah? So, what's going on there? Watch this. If I have my thumb pointing in the direction of my torque, which way are my fingers curling? They're going like that, aren't they? So, when the vector torque is like that, the turning effect is like your fingers. So if the vector torque is upward, the thing's going to turn that way. If the vector force in that direction, the thing is going to want to turn that way. If the vector torque is down, the thing is going to want to turn in that direction. So if I can look at a system like this, so let's say this is a three-dimensional, sorry, I lost my pen. This is a three-dimensional bit. So here's my turning axis, and here's my force, and it's at the end here. So what's going to happen is this thing is going to tend to want to turn in a clockwise direction. And what I'd say is, R cross F means that in a three-dimensional drawing, my vector torque is downwards. So there's my vector torque going down, and put my thumb on the vector torque, and I get the same answer. So it's a way of keeping track. It's a way of bookkeeping. So we need a direction for our vector torque. We need and we need to know, is that clockwise or counterclockwise thing. We can figure it out. Determine the torque about this axis O caused by this force. So this is not a vector. We're gonna write it down, but we're going to say, well, our torque is equal to R cross F. And in dot products, as we'll get to in a couple of minutes, the order matters, whereas in a dot product the order doesn't matter. In a cross product the order matters, and it is R cross F. It's not F cross R. But this, for today's purpose, is equal to the magnitude of R times the magnitude of F times the sine of the angle between. So this would equal, in this case, it would be 3 meters times 7 newtons times the sine of 60 degrees. So this will be 21 sine 60. And if I dig my calculator out, 21 sine 60. So 21 sine 60. And that's going to equal something like 18.2. And what's it going to be? What are the units going to be for torque? It's good. Well, it's going to be the SI equivalent of foot-pounds, which will be the Newton meters. Yeah. Now, as engineers, so this is a philosophical thing. As engineers, you will be faced with imperial units in certain industries. If you go into digital electronics, you'll never see imperial units. If you go into power generation, you might. Because the people who want to buy your generator, or the people who want to buy your motor, may well deal in foot-pounds. But you can spend, in certain industries, you'll spend your entire life and never see imperial units, and in other bits of engineering, you'll use it every day. It's just the way it is. In Europe, not the case. In Europe, basically, has got rid of all the imperial units. And this leads to some problems, as I may have told you with work. You know, there was a situation with a Mars lander where it crashed into Mars, and the reason why it crashed was because one team was working in foot-pounds and the other team was working in Newton meters. And they just handed off the digital number to each other. They handed off the numerical value from one program to the other, but it was interpreted in terms of different units. It was a disaster. So we've got to be careful about it. So that, in essence, I just touched on torque here. I want to talk a little bit about some other relationships. We said linearly that the sum of the forces equals ma. Well, the sum of the torques is equal to I times alpha, where I is the moment of inertia. And this is the angular acceleration. And moment of inertia is kind of like the angular mass. It's like and so then the book goes off and we talk more about moments of inertia, because they want to handle that before they get back to torque. So we touch on torque and then we come back to torque later on next chapter. Here's a classic physical situation. A cylinder with a 3 meter radius is rotated about its turning axis O. So the turning axis is through the middle of this drum with a tangential force of 7 newtons. The moment of inertia about the turning axis O is 6 kilogram meters squared. What is the angular acceleration of this cylinder? So I want to know what the alpha is. You apply a force to a mass and you get an acceleration. You apply a torque to a moment of inertia and you get an angular acceleration. The drum will start rotating and rotate faster and faster and faster while ever the torque is applied. How can you do this in practical terms? You basically get a piece of string and you wrap it around the drum about 12 times and you pull. And the nice thing about that is no matter where you pull, the rope will always form 90 degrees. So it will always be a tangential force. If I was to nail the piece of string there, I could pull at some wacky angle. But if I wrap the string around them, I can be tangential. So in some questions I've seen, they don't say it's tangential, just say you wrap a piece of string around a drum and pull. And they leave you to visualize, oh, that's going to be a tangential force. So it's a little bit of visualization there. But basically what we say is, well, the sum of the forces equals MA linearly, so the sum of the torques equals I alpha. And the torque, of course, well, I know its value, it's the force times the perpendicular lever arm. Let's just remind ourselves with that. And this equals my moment of inertia times my alpha. Well, in this case, I know the force is 7 newtons. And I know my perpendicular distance is 3 meters. And that equals my I, 6 kilogram meter squared. We'll get to that in a minute. That's a weird kind of unit. Times alpha. So alpha is going to equal 21 over 6, which is half of 7, which is 3.5, and the unit's going to be radians per second squared. Okay. So there's a few things going on. I don't know about you, but around about now I'd be feeling a bit uneasy because it's unfamiliar. It's not because it's mathematically hard, it's a piece of cake. It's unfamiliar. So let's just dwell a little bit. So remember, torques, the force must be perpendicular to the distance that you give. Okay, there can't be any old angle. So get that drilled in. With work, they had to be in line. Now they've got to be at 90 degrees to each other. However you do it, you've got to do it. And then the moment of inertia, well, moment of inertia is angular mass. So it's kilograms are going to be in there. But it turns out, as we'll see in a minute, there's going to be also the distance squared. Well, we'll get to that in a minute. Okay, so let's talk about moment of inertia. We don't justify this. We just pull it out of thin air. But basically, what we say is the angular mass, the moment of inertia, depends upon the mass, but it also depends upon where the mass is positioned. And it turns out it's not a linear relationship with that lever arm. It's not a linear relationship with that distance from the turning axis. It is a squared relationship. So the distance really, really matters. The mass matters, but the distance really, really matters. If I take the same mass and simply move it twice as far away from my axis of rotation, I have quadrupled the rotational inertia, which is what moment of inertia is. It's your rotational inertia. I'm 4 times more sluggish to angularly accelerate if that mass is twice as far away. I'm 9 times more reluctant to angularly accelerate if I move that mass 3 times farther away. I'm 16 times more reluctant to angularly accelerate if I move that mass 4 times further away. So if you want to make something reluctant to rotate, move the mass away. Don't make the mass heavier. Move the mass away. And you saw that when in that axis when you were spinning on the chair and move your arms out. You could see that, well, that's not a good example. You saw that when you were trying to do the wands. Yeah? It was much harder to do the wand where the masses were further away. Much harder. You weren't changing the mass, you were just moving it further away. And it was, 10 times harder to get it going. It was really hard. So there we have it. So what do we do on a simple system? We basically have discrete masses, and we're going to say, what's the distance to the first mass? Multiply that mass by that distance squared. Where's the second mass? Multiply that mass by that distance squared. Third mass, multiply that mass by that distance squared. Add them all up. That's what that's saying. So I can dress it up a bit and do a little bit of, testing. So rather than just giving you 3 masses and 3 distances, I give you a diagram to interpret. And so we have 3 masses here, and we say, I know that my moment of inertia, my I, is equal to the sum of each mass times each distance squared. And it's about a turning axis. I've got to say where it's about. So it's about this turning axis. I should say I around 0. So this would be I around 0 is equal to, just pick them, it doesn't matter, 4. I'll do the bottom one first. That's going to be 4. And this distance is not minus 3. It doesn't matter. The direction doesn't matter. All that matters is the magnitude. So that's 3 squared plus. And this one here is 5. And that's going to be 2 squared. And this one here is, it's that. And it's going to be 3 times that distance squared. And I can actually find that distance just over to one side. It's basically 1, 2, 3, 4 units up. And it's 1, 2, 3 units across. And that's a right angle. I didn't draw it very much like a right angle. With a bit of practice, people recognize the 3, 4, 5 right triangle. And if you don't recognize it, you say, well, this distance r, you say r squared equals a squared plus b squared, r squared equals 3 squared plus 4 squared, r squared equals 25, r is equal to 5. So you can figure it out mathematically, or you can recognize it. But we know this is 5, and we've got to square it. And then what we do is we say, okay, well, I0 is equal to 3 3s are 9, so it's 4 times 9 plus 5 times 4 plus 3 times 25. Then I go, I0 is equal to 3 9s are 27, 4 9s are 36 plus 20 plus 75. I0 is equal to 75, 95, 126, I think. Oh, no. 75, 95, not 126, 131, I think. 131. And now what will the units be? Well, look up here at your equation. Kilogram and then meters squared. Cool. Now, that's that object's moment of inertia about that rotating axis. Okay, I'm going to change the problem. I'm going to say that's my rotating axis. We'll call that O dash. So my moment of inertia about O dash is equal to the sum of MIRI squared. My moment of inertia about that new axis is equal to, well, it's going to be 3. Well, let's do them in the same order. So it's going to be 4. But now 4 is not 3 units away. 4 is 1, 2, 3, 4, 5, 6, 7. 7 units away. That's 7 squared. And then I take my second mass, which was the 5 kilograms, but now I want that distance. So that would be 5 times, well, let's put it down. It's going to be 2 squared plus 4 squared I want the square root of that to get that distance, but I've got to square it, so it's going to be 2 squared times 4, plus 4 squared. Everybody okay on that? Using Pythagoras. And then on this guy, I have it's 3 times, and this is going to be 3 times 3 by the look of things. 3 times 3 squared. So then I know around my new axis is 4 times 7 sevens are 49 plus 5 times 2 2s are 4 and 4 4s are 16. Add them together and we get 20. And then we get 27. Oh, I did that all hung in my head, sorry. So that's going to be 160, 3 9s 27, 4 9s are 36, 196 plus 100 plus 27. So that would be 296, 296, 323. So there's my answer about that turning axis. It's much more reluctant to rotate about the second axis than it was about the first axis. And that's because the first axis was kind of like in between the other masses. There was a bit of a distance there, but not so much distance there, and 3 relatively short distances. Whereas for the second rotating axis, I had a very long distance, and that kind of killed me, and then a relatively long distance, and then a short distance. So longer distances, 7 squared, there's nothing even close to a 7 squared there. And there's a 3 squared, there's a 3 squared there, and so on. So the further your axis is away from where the masses are, the more reluctant those masses are to rotate about that point. So what am I visualizing here? I'm visualizing actually like a perspex wheel with a rotating axis and a mass here and a mass there and a mass there kind of thing, And if I move these to different positions or I try to get it to rotate about a different point, I'll get different willingnesses to accelerate. Willingnesses to speed up rotation or willingnesses to slow down rotation. It works both ways. Moment of inertia for a distributed mass system. So for a distributed mass system, for a distributed mass system, well, it's now kind of like an object. Could be a cloud, could be a potato. And what we do is we get our potato and we pick an axis through it. And we say, what's the moment of inertia about that axis? We know it's going to be different than the moment of inertia about that axis or the moment of inertia about that axis. We know that we can pick any old axis and we'll get a different value for this. But we can work it out. And what we say is, well, in the limit, as my little bit of mass, or divide this thing up into little cubes of mass, as my little bit of mass goes to 0, then the sum of Ri squared times delta m, little bit of mass, equals the integral of r squared times delta m for each one of those little squares. Calculus. And we use this calculus, we're going to use this calculus on one specific example. And that's going to be what we call the solid cylinder. Now, we have the solid cylinder. And I am interested in the moment of inertia about the axis through its middle, circular center. I'm not going to tell you about the axis through the sides or through some weird angle. I'm going to go through the symmetrical circular center because it's mathematically easier. For calculus, you need symmetries. There are other things I could do. I could do a hollow hoop. And the deal with a hollow hoop is that the thickness of the material is not very thick. It's a pipe, basically. And the deal is it's not a thick pipe, it's a shallow pipe. It's a thin pipe. And again, we're interested in the circular axis. So I want my moment of inertia about here. I want my moment of inertia about there. Not through the edges. Mathematically, that's harder to do. And then the other, so this is a hollow hoop. And then the third one we have is and I draw it like a billiard ball with like a little reflection from it. A solid sphere. Not a shell, but a solid sphere. Not an eggshell, but a solid sphere. Dense all the way through. And those are my three common playthings that I'll use mathematically in physics problems. And frankly, over the years, I've learned actually, especially what can you call these? I could call that solid cylinder a disc. It's kind of like a disc. I could call the hollow hoop a washer, a ring, and I stopped. Because what I found was that for a fair number of our students, then what you called it kind of like was very confusing. What colloquially meant was very clear to me was not very clear to them. And so I'm making a trade-off here, and that is I'm saying I will only use the terms solid cylinder, hollow hoop, or solid sphere on your test. I won't use disc, I won't use washer, I won't use ring. But recognize the fact that in the broader community, people will say disc, and they mean solid cylinder that's kind of flat. But the problem is you have a compact disc which has a hole in the middle. Shouldn't it be a compact washer? We're very loose with our language. And I don't want that to be the issue for us. So I will stick to those three terminologies. Solid cylinder, hollow hoop, solid sphere. There may be some homework questions where it's still got disc in, but I doubt it. I think I've gone through and got rid of all those and reworked them. Using the method of calculus, as shown in physics class, show that the moment of inertia of a solid cylinder about an axis through its circular center is a half mr squared. This will be a test question. There's the video is already online, so you can watch that to your heart's content. But I'm going to go through it again today. So the first thing is to visualize it. So there's the solid cylinder, and I'm interested in that turning axis there. And I need to have a T for thickness, and I need a big R for radius. I need a big M for mass, and I'm kind of on my way. So what bit do we have to do? We have to envisage a sleeve of this. Think back about when we had the triangle. We had our shape and we envisaged a slice. Well, now we have our shape, which is circularly symmetrical about our turning axis. So rather than a linear slice, we have a sleeve slice. Yeah, it's like an onion. It's like a ring of an onion. Got to give this some terminology. So that will be little r, and then it's got a certain width, which is going to go to 0. We'll call that dr. And what I'm going to do is I'm going to integrate over all these slices. I'm going to divide this up into 1,000,000 slices and go from the smallest slice to the biggest slice. So there's my setup, basically. And then I say, well, my moment of inertia is equal to the sum of, what was it, r squared m? Yeah. And this equals the integral of r squared dm. Now again, I don't have a, as I stand here, how do I know it's not m d squared r? It's just the way it is. It's r squared dm. A little bit of mass. Okay, I have no idea how to do that, so I need to convert. So down here I'll do the conversion. So I'm going to say, well, dm is equal to something. And physics, dm is the little bit of mass of this. So this has a mass dm, and this is the mass of the whole thing. So I'm doing the little bit of mass of the slice. It's a uniform density, so this will equal the sleeve volume multiplied by the density. And it's the volume density. We've talked before about the linear density for a rod. We talked about the area density for a triangle. This is a three-dimensional shape. We'll call it the volume density. All I've got to do is work this out. Well, let's just say dm is equal to the sleeve volume, and I'm going to draw and then erase, because I'm going to not have enough space if I'm not careful. I'm going to cut this thing, and I'm going to unroll it. And it will be, if you ever made Swiss rolls or, whatever, you take some, you know what I'm talking about. Unroll it, cut it, and then unroll it. And basically that dimension there is t. And this dimension here is dr. And then what's this dimension across the top? You don't know the number of it, but can you give me some letters for it? No x on this thing. 2r's not going to do it. Look at the shape of this. 2 pi r. Now we're cheating a little bit, aren't we? Because r's to the beginning inside of this slice, well, yeah, but as dr gets less and less, it doesn't matter. But it's the circumference, isn't it? We took the circumference and rolled it. So that means that my sleeve volume is equal to t times 2 pi r times dr. Simple as that. Okay? I'm going to erase now, because that bit served its purpose, and I need the space later on, I think, anyway. Now I've got to find the density of the entire thing. So let's have a look at this. So that's that bit. Then I come along. Volume density. Well, the volume density is the total mass over the total volume. So dm is equal to t times 2 pi r times dr times m over. Now, this is a right cylinder. We've practiced that, haven't we? We've practiced the equation for a right cylinder. It's the height, let's call it t, perpendicular distance times the area, circular area, pi, not times little r squared, it's big R squared, pi r squared. So we've got to be careful here about what's a constant and what's a variable. It's the total mass over the total volume, and the total volume is bounded by big R, yeah? Because the radius is big R. That's a mistake that people will sometimes make. Now, it may be when I'm doing my integral, I'm going to have a big R in there again, but for the moment, I'm just being careful. So let's have a look. Let's change colour pens, and let's just some cancelling if I can. So that t cancels with that t, that's nice, and that pi cancels with that pi, but that's about it. So I'm going to say, well, dm is equal to, let's put the 2 at the front, let's put the m next, let's put the r dr over r squared. So it's the same principle that I've used 3 times now. This is the 3rd time I'm using it. I'm trying to integrate with respect to the wrong thing. Let's do a conversion. And I take this up to here, and life gets good. Because I say, well, I is equal to the integral of r squared, not dm, but 2mr over r big R squared. Notice I nearly put down the little r squared, big R squared dr. And then we take out everything that's constant, so I is equal to, well, 2's a constant, and big M's a constant, and r squared is a constant. Times the integral. Well, r squared times little r is r cubed dr. And at this point I stop and I just make sure that I've got everything accounted for. My r's there, my r squared and my r become r cubed, and my dr is my dr, and my 2 is there, and my m is there, and my big R squared is there. Good. Oh, well, this is going to be I is equal to 2m over r squared. R to the 4th over 4? Yeah. That's my integral. And now the limits. Commit. What limits do you think we should put down for this integral? Look at what we're integrating with respect to. What letter is it? And then look at where that is in your diagram and say, how small can that be? And how big can that be? And if you don't know the numerical value, put down the letter value. So commit. Well, you're going to write down a letter or something, a number or a letter, for the smallest limit of integration. And put down something for the biggest limit of integration. See if you can see it. So look at what we're looking at, which is this r. We're looking for the integration with respect to little r, dr, with respect to little r. And what's the smallest value that r can have? And then what's the biggest value that r can have? So it's going to be, the smallest is going to be 0. And what's the biggest? Yeah, you don't know the value of it, but you know we've been calling it big R. Okay? That's the second place where people will put down the wrong limits of integration. And then we go, well, I is equal to 2m over big R squared. And then it's just, big R to the 4th over 4 minus 0 to the 4th over 4. So I is equal to 2m r to the 4th over 4r squared, which equals 1/2 m big R squared. And there's our expression. So I'll leave you a second just to digest that for a second or so. So, and this is an upcoming test question. As I say, I'm willing to tell you it's an upcoming test question because I want you to go for the points, because I want you to develop these skills. And my theory is that if you go for it, you'll learn it, and then when I give you something a bit more complicated, it's not that much more complicated. But if you never go for it, you quickly get to the stage where all that stuff is just beyond where you're thinking. So you don't make that transition. So I'm paying you to make that transition by saying, hey, I will guarantee it's on the test. If you want the points, you got to do it. You got to show me it. And so I'm quite strict. So I expect to see a diagram. I expect to see this working out clearly. Clearly. I don't expect to see that and that. You've got to justify. I want you to show me that, oh yeah, this is sleeve volume times the volume density. You've got to show me the physics thinking. This is not about memorization. This is about physics thinking. So you've got to show me that, and then you bring it up here and you do this, and you've got to show me the limits. But what I notice is people will remember that. There's no diagram. They'll substitute that in. They'll get an answer and they go, I'm done. And that's not what I'm after. No credit for that. The method of calculus, as shown in class, is this. want to see it. Okay. And I'd gladly give you the points, but I won't give you the points if you don't show me that, you know. I'm quite strict on it. In truth, if you were to watch me do this in 3 different ways, I would have 3 different sets of language, but it all mean the same thing. I don't remember this. I don't go home and learn this. I just know, oh yeah, I need to work out the little bit of mass. How do I do it? Oh yeah, it's going to be the little bit of volume multiplied by the volume density, you know. So I figure it out. The language will change. Sometimes I'll say a little volume rather than sleeve volume, you know, but the principle is the same. So I don't remember the steps. I remember the method. And that's what you need to do. You need to get the method. In truth, if you said, oh, I'm just going to assume this is so thin because it's a uniform depth, I'm just going to say it's an area. So I'm going to say, oh, it's the sleeve area times the area density. It's the sleeve area times the area density. You'll get the same answer. You know, that can work. I even used to do it that way. But now I'm becoming purer, and I say it's a 3-dimensional shape. Let's recognize it as 3 dimensions. So that's going to be on the test. So learn it and enjoy the points. But you've got to show me the bits. When the moment of inertia of a solid cylinder of 9 kilograms and 3 meters radius and 2 meters thickness about the axis of its center. What is the so now I might just ask you what the moment of inertia is. I expect you to know 3 equations. I expect you to know that I for a solid cylinder is equal to 1/2 mr squared. I expect you to know that I for a hollow hoop is equal to mr squared. I expect to know that I for a solid sphere is 2/5 mr squared. Now the first one I might ask you to develop using the method of calculus as shown in class. But the other 2 I wouldn't. But they can come up in problems. So know these. And in this case it says, what is the moment of inertia of a solid cylinder? So I solid cylinder is equal to 1/2 mr squared. So I solid cylinder is equal to 1/2 times 9 times 3 squared. So I solid cylinder is equal to 1/2 times 81. So 1/2 solid cylinder is equal to what? 40.5. And what the unit's going to be? Well, it's going to be kilograms meters squared. So, and so on. From this, you can see which is the biggest for a given mass and a given radius. Which is the biggest moment of inertia? Can you order them for me? Which is the biggest? Is it this or this or this? Which is going to for a given mass, call your mass 1, and a given radius, call your radius 1. Which gives you the biggest value? 1, 2, or 3? 2. So this is the biggest. So I hollow hoop is bigger than, which is the next one in line? It's going to be 2.5 over 5 versus 2 over 5. So it's going to be I solid cylinder, which is bigger than I solid sphere. So, you know, however you want to remember it, you can visualize it. Is my thing is bigger than, is my thing is bigger than, is my thing. That's useful to remember. So in a race, like you saw in that lab, the hollow hoop lost to the solid cylinder. Because its moment of inertia was bigger, it was more reluctant to start rolling. So the hollow hoop lost. I apologize for this. This was I don't know what I was thinking. This is going to be 1/2. And this is 2/5. I want everything to the base 10 so we could, but that's not the way you'll ever see them in a book. So, solid cylinder has a radius 4 meters and a mass of 2 kilograms. What is its moment of inertia? About its circular axis. All of these are about an axis through the middle, through this axis of symmetry, we'll call it. So solid cylinder, man, I'm going to not do the solid cylinder. Oh, I'm not going to do the solid cylinder all the time. Hollow hoop. So for the hollow hoop, I have a mass is equal to 2 kilograms and the R is equal to 4 meters. Then I'll say I hollow hoop is equal to mr squared, which equals 2 times 4 squared, which equals 2 times 16 is 32 kilograms per meter squared. Sorry, not kilograms per meter squared. Kilogram meter squared. Kilogram meter squared, yeah. Let's say we want to go through an axis which is not through the symmetrical center. Well, let me back off a little bit. So first of all, if I take a potato, it has a center of mass. Agreed? We did that before. And the center of mass will be somewhere in the middle of it. And an axis, well, I could pick a series of axes that pass through that center of mass. And I would get different values for I, because of the shape of the thing. There'd be different values of I. Think of a pen. You have a value of I in that axis going through the center of mass. You'd have a value of I in that axis going through the center of mass. I have a value of I going through that axis through the center of mass. This is the one with the least I, because the mass is all close to the axis. So it's easier to spin that way than it is to spin that way. Okay. So the moment of inertia, so the center of mass is there for an object, and we can put a whole bunch of axes through there, and we'll have different values of I in different axes going through the center of mass. But there's going to be one that's the lowest center of mass. Well, it doesn't really matter about that. If I know the moment of axis through a center of mass, let's call it ICM, and I want to find the moment of inertia about another axis which is parallel, so I can't take that and then take that. I have no idea about the I here compared with the I there. But if I take that and I take that, if I know this one, I can find that one, because they're parallel to each other. It's called the parallel axis theorem, which is often what we want. So I simply say the moment of inertia about my new axis, I0, is equal to the moment of inertia about my center of mass, ICM, plus, and it's going to be something to do with mass and something to do with separations. And we know that the units have to be consistent, so kilogram meters squared can be equal to something which is kilogram meters squared plus, and we know from dimensions on chapter 1 that this thing should be kilogram meters squared. So by all means, you might get confused about, is there a numerical coefficient in front of this? Because dimensions don't tell you that, and there isn't in this case. Well, it's 1 if there is one. But don't get confused about what the parameters must be. It must be mass times distance squared. It's got to be, because dimensions tell you it's got to be. So a body has 4 kilogram moment of inertia about its center of mass. So I center of mass is equal to 6 kilogram meters squared. What is the moment of inertia of the body about another point O that is located 2 meters from there. So I say IO is equal to I centre of mass plus the mass times the separation squared. So IO is equal to, what was the I centre of mass? 6. Plus the mass, 4, times the separation squared, 2 squared. IO is equal to 6 plus, that's going to be 4 4s are 16, 16. IO is equal to 22 kilogram meters squared. Boom. I'm going to stop there because we're running out of